SwayamPrabha. Digital India. Educated India.
So, we'll continue our discussion on cylindrical deep drawing. So, in the last lecture, we were discussing about the theoretical models to calculate radial stress, then cup wall stress, and then maybe a circumferential stress also when you do a single stage deep drawing process. And after that, we have seen one small subsection on how this limit drawing ratio or limiting draw ratio, how is it going to get affected by sheet anisotropy. If you consider sheet as isotropic material or anisotropic material, okay, and specifically when plastic strain ratio is greater than 1 or greater than 1. So, how LDR is going to change, we have seen in last class, and at the end of that the change in thickness delta T by T, what is the change in thickness during bending and unbending while stretching. Okay, that is what is a situation seen in deep drawing. That also we have seen in the last class, and how this LDR is related to plastic strain ratio. What do we need? What are the conditions for R and for your rho by T bend ratio and the friction coefficient of friction, isn't it? How these three, how do we need to control it to have particular LDR is what we stopped in last class. And just before we go ahead in today's class, there was one small confusion in the last class that these nomenclatures were not written properly with respect to your effect of die radius. So, while calculating sigma R, okay, so we took effect of friction separately as compared to strain hardening, right. So, in effect of friction there are two parts, one is effect of die radius and the friction between blank holder, die and the sheet. So, in the first part, effect of die radius, this was not properly written in the last slide. So, just this is for you to for us to just to refresh and just minimize the errors. So, from this we can integrate it in the die corner region, and we can get this particular equation for sigma phi, which is nothing but your stress in the cup wall, sigma R exponential mu into pi by 2, that can be obtained from this equation, from this integration. Okay, so just one small change that we have, we want to look into it. Okay, so now let us go ahead in this particular chapter. So, today's small section, first section, we are going to see 3-4 important small sections to wind up this particular chapter. So, first one is estimation of cup height. So, this is an approximate estimation of cup height. Okay, so when you do deep drawing of circular cup, what is the cup height at any stage? How can we calculate it? So, let us consider the initial sheet of let us say radius R0 and let us say thickness T0. Okay, let us consider a sheet like this, and then the sheet is drawn to a cup like this. So, on the left hand side I am drawing, okay, so the same sheet, okay, which is practically it would be something like this. So, you have a cup wall and there will be slight thickening and you will be slight thinning at the end maybe. Okay, so you will see that here you will have a larger thickness, let us say T, here thickness would be equal to T0, and in the corner you may have less than T0, okay, greater than T0 you can see. So, in the cup edge region, okay, so because of thickening you may have thickness greater than T0, here it is equal to T0 and here it is less than T0 actually speaking, but we are going to neglect all such changes and we are going to assume that the thickness is going to remain same T0 as that of T0 here at any stage of deformation, and we want to find this h height, and let us say the inner radius is Ri. Okay, your cup radius is Ri. So, initial sheet radius is R0 cup radius is Ri, so R naught should be converted to Ri, okay, and the thickness remaining same, T naught remaining is T naught, and his H is the cup height at any stage. So what I can do is I can equate volumes in both the stages, initial and intermediate. So pi R naught square T naught would be equal to pi Ri square T naught plus 2 pi Ri T naught H. So I am going to neglect the change in like your corner. Corner is not considered here, okay. So it's going to be a straight wall and it is connected to the cup bottom. So this is for the side the cup wall, and sorry, this is for the your cup bottom, and this is for the side cup wall, okay. And from this you can see that T naught will go off because we are going to consider it the same. Pi also goes off, okay. So and from this you can get H. H will be given by Ri by 2 into R naught by Ri whole square minus 1. So where R naught by Ri is our own drawing ratio. So dr, right. R naught is your initial cup radius. You can also keep diameter, okay. And then this is your sheet. This is a sheet radius. This is a cup radius Ri. So ignoring a change in thickness in the cup wall, only approximate value of H can be estimated. So this is what I was telling you. So we are going to neglect this change in thickness in the cup wall. So instead we are going to get an approximate value of H. It will not be fully accurate, but still it is fair to have some quick idea of what would be H at any stage. So now some one or two important points we can understand from this. Suppose if you keep R naught by Ri as 2.2. So in the previous section, okay, we derived that LDR is almost equal to 2.72, and then we said that this is theoretically high, okay. So instead of that, practically if you take eta as, this is eta is equal to 1, so this case will come if you take eta is equal to 1. Suppose if you take eta as equal to 0.6 to 0.7, we said that LDR can have between 2 to let us say 2.2. So and we worked out that if it is 0.7 it is 2, okay. If it is 0.7 it is close to 2. Okay, so you can imagine about LDR can be about 0.2 for 2 to 2.2 for practical case. This would be the case. This is highly theoretical in nature, okay. So LDR is 2 to 2.2 is advisable for us, right. So if you keep R naught by Ri as 2.2 in this, so you will get H by Ri as 1.9, okay. So you can substitute. So Ri by 2 into 2.2, this would be 2.2 the whole square minus 1, okay, and you will see that H by Ri, this H by Ri you take it down denominator, you will get it as 1.9, which is less than 2, or height to diameter ratio. Suppose H by Ri can be converted to H by D, this is less than 2, this would be less than 1, this would be less than 1. So what does it indicate? Indicates that the height that can be cup can be drawn, okay, maximum value is going to be equal to the top diameter of the your cup, okay. So you cannot have more than that in one stage. So H by D less than 1 indicates that deeper cups can be obtained only by redrawing operation, okay. If you want to draw more than this, okay, so then you have to go for redrawing operations. So redrawing basically means suppose this cup is formed, okay, this is drawn again, okay. So this is the flat sheet to this cup is 1, and this cup is further made in the form of another cup of different dimensions, that's all. So this is basically your redrawing, okay. So redrawing means again and again you draw it until you make your actual cup, okay. So now when we go for redrawing of cylindrical cups, this can be actually divided into two varieties. So one is forward redrawing, the other one is reverse redrawing, okay. Forward redrawing and reverse redrawing, okay. These are the two types. Like for example, we have forward extrusion and backward extrusion, or direct extrusion, indirect extrusion. So similarly we have forward redrawing and reverse redrawing, okay. Let us pick up this forward redrawing first and develop some simple expression for this, okay. So I have drawn here the schematic of forward redrawing. You will see that, so what are the things available for us? So you have a punch, okay, you have a die. So naturally, so on the die you are going to keep your drawn cup. The first level of drawing is done. So you are going to have a cup that is located on the die like this, it is located on the die like this. So, your cup is like this first, your cup is actually located like this on the die. Okay. So, now on that you are going to push your punch to come down. Okay. The punch has to be displaced in this way, and this the cup, drawn cup is actually positioned above die by using this retainer. Otherwise, you can say it is a blank holder only. Okay. And once you are going to push it down, so you will see that the bottom part of the cup is actually drawn. Okay. So, that is how it is. So, your sheet is actually going to be drawn to make this particular part of the cup. So, the upper part, this is belongs to the first stage, and the one which is now done by this die belongs to the second stage here. So, this would be first stage, this would be the second stage of drawing. Okay. The second cup that is formed, this is the second cup that would be formed. Okay. So, basically you have to push it, punch down such that this wall is going to bend here, unbend here, bend here and unbend here. So, that is how it is to be. So, this wall region has to come down, it has to bend, it has to unbend, it has to bend and it has to unbend to form a full cup wall here. Finally, you will have a cup of radius R2. Okay. So, initial cup radius is R1, new cup radius is R2. If this is sufficient, that is fair, but if this is not sufficient, then R2 will be again drawn to next cup with radius R3, the same way. Okay. So, in that case this would become R2, this fellow will become R3 like that. Okay. So, that is the point here, and so now the question here is, so how are we going to model it using some simple mechanics which we already discussed. Okay. So, that is what is this slide is going to show, and the main aim of this particular derivation is to get this F. So, the punch is actually getting displaced, but the F has to be found out, that is the punch force have to be found out for forward redrawing. Okay. So, initial cup radius is R1, new cup radius is R2, let us take thickness as T and let us assume the thickness is not changing. In the usual way we are going to do that, and so initially we know sigma phi, cup wall stress in the cup wall. We already derived that. So, now you imagine that there is one tension because of that, that is T phi. Okay. Let T phi be the tension in the cup wall between the bottom of the punch, that is this portion, bottom of the punch and the die. Okay. Between the bottom of the punch and the die there is a cup wall, and the cup wall you have a tension of T phi. Okay. That is given by the sigma phi. Okay. Sigma phi is, we are aware of that in the previous lecture. So, now the force exerted by the punch is simply given by F is equal to 2 pi R2 times T phi, 2 pi R2 times T phi. Okay. So, now this wall tension actually you will see that it is going to depend on the severity of drawing. Severity of drawing means it depends on what value of R1 is converted into what value of R2, which is given by R1 by R2, which is otherwise called as like for example some sort of reduction. This is the reduction you have, this is the reduction in the cup you have at the end of second stage. Okay. So, R1 becomes R2. So, how severe is this? Is it like 100 to 50 or 100 to 30? That is the point. So, 100 mm radius is converted into 30 mm radius, or 100 mm radius is converted into 50 mm radius. So, that this T phi actually depends on this ratio. So, what we are going to do is we are not going to develop this equation, rather this is actually taken as it is directly. Okay. And I am going to say that by assuming yield tension as T bar, the wall tension is given by T phi is equal to T bar ln of R1 by R2. Okay. This portion is actually not derived, let us accept it right now. Okay. T phi depends on R1 by R2 by following this equation. T phi is equal to T bar, which is nothing but your yield tension ln of R1 by R2. This yield tension is given by sigma F into T, which is the usual definition we have right from the beginning. Okay. So, T phi now becomes sigma F times T times ln of R1 by R2. Okay. So, this T phi can be substituted in this equation. So, F becomes 2 pi R2 into T phi is sigma F into T into ln of R1 by R2. This fellow is nothing but my T phi. Okay. So, drawing force in forward redrawing can be obtained by the simple expression 2 pi r2 sigma f t into ln of r1 by r2, where all are known things like r2 would be your new cup radius, rf is only material property you have here, which is nothing but the flow strength of the material, okay, and t is your sheet thickness, which is assumed constant, and r1 by r2 is nothing but the ratio. Your tells how much is the reduction, that will be your r1 by r2. Anyway, r1 is basically the initial cup radius, which is what is given here. So, you know all these values, if you substitute it, you will get a force. Okay, this would be the punch force required for forward redrawing. So, this is a simple equation, and of course, you know that the sigma f can be kept as a constant value, or it can be made as a function of strain to consider strain hardening. It can be made as a function of strain rate. Okay, sigma f can be a function of strain, you can make it as a function of strain rate also, or you want to keep it as an average one, sigma f average, like what we have done in the previous section, that is also possible. So, all are possible here, but the form of the equation will remain same. It is very simple to use, 2 pi r2 into sigma f t ln of r1 by r2. Okay. So, now we are not going to keep it so simple. So, what we are going to do is, so we are going to now introduce one more addition to this equation, that is nothing but the change in tension due to bending and unbending during this redrawing operation. There will be some change in tension, this T phi, this phi, this value T phi is going to have an addition of one particular value, that is because of bending and unbending during this drawing operation. So, what is it? Again, we are not going to derive, this is actually taken from a different chapter, okay, so which is not derived, but then let us accept it, let us go ahead in the derivation. So, because of either a bending or unbending, so for one bending or unbending during forward redrawing, the tension increase is given by this equation. This equation again is not derived, I am telling, this is for us to take care. Okay, T delta T phi, del T phi is approximately equal to sigma f, usual flow stress, T square, where T is nothing but your cup thickness, divided by 4 into rho, okay, where rho is your this one, here it is written, this is rho. Okay, so this equation is valid for one bend, either one bend or one unbend. Okay. So, now what we are going to do is this T phi, this delta T phi is going to be added to this T phi, okay, to get f. So, it is going to be f is equal to 2 pi r2 into T phi plus del T phi, that is going to be the case. But there is one small thing in this, that in this forward redrawing, if you see the same schematic, bend and unbend together are actually equal to 4. So, you have one bend and then unbend, another bend, another unbend. So, one bend is happening here, and then that fellow is actually unbending, another bending, another unbending. So, by considering all this, what I am going to do is, we find 2 bends and 2 unbends are required in this forward redrawing. Therefore, my original equation f is equal to 2 pi r2 T phi becomes f is equal to 2 pi r2 into T phi plus 4 times delta T phi. Okay. So, this is for either a bend or unbend. So, there are 4 such things, 4 such activities. So, I am going to multiply this by 4, T phi by 4, and then I will add it with this T phi to get my f. Okay. So, what will I get? I will get 2 pi r2. Okay. So, I will get 2 pi r2, f is equal to 2 pi r2 into T phi. So, what is a T phi? T phi is already we calculated it, T phi is sigma f t ln of r1 by r2, right. Sigma f t ln of r1 by r2 plus 4 times this fellow. So, sigma f t square divided by rho, 4 will be cancelled. So, now this will give you sigma f r2, sigma f t is common. So, I am taking it out. This fellow will have only r1 by ln of r1 by r2 and then t by rho, or it can also written as 1 by, this can also be written as 1 divided by rho by t. Okay, that also 1 divided by rho by t, that also where rho by t is nothing but our own bend ratio. Okay. So, what we are doing is, because of bending and unbending during this particular process, there will be some change in tension, that is as a cumulative thing. It can be quantified by sigma f T square by 4 rho if you have either one bend or one unbend. Now, there are 4 such activities. So, 4 del T phi would be the right additional term to this f. Okay. That is why it is going to become 2 pi r2 T phi plus 4 del T phi. Okay. So, and then if you substitute T phi value into this, you will get this equation, which will be simplified to this equation. F is equal to 2 pi r2 sigma f t into ln of r1 by r2 plus t by rho r plus 1 by rho by t. Okay. Where you know that r1 is nothing but the first cup radius, this is the new cup radius, t is a thickness, rho is the corner your radius, you know that the die corner radius, and sigma f is only material property, nothing but the flow stress, and T is the thickness, all are known. So, now this R1 by R2, if it increases, that is why I gave an example, it is 100 by 50 or 100 by 50 or 100 by 30. Okay, let us say if it is 100 by 50 or 100 by 30. So, R1 by R2, if it increases, that means reduction is going to be larger, which means there are a lot of chances that your force is going to increase. That is what is given by this equation. And at the same time, rho by T, if you see, if rho by T decreases, it is a denominator, rho by T decreases, there are chances that F is going to increase. If rho by T decreases, there are chances that your F can increase. So, anyway, finally, this is the drawing force in forward redrawing by considering the change in tension, So, this equation and the previous equation, 2 pi r2 into T phi, or this one 2 pi r2 into sigma f into T into ln of r1 by r2. These two are two different equations for getting drawing force in forward redrawing. So, either this equation or the previous equation. These two equations can be used for calculation, but this equation is going to be little bit basically more accurate for us, for the simple reason that you are going to have, this equation is going to be more accurate because you are going to have change in tension coming into picture here as compared to the previous equation. So, this is what is all about forward redrawing. Okay. So, now let us go to reverse redrawing. And let us see what change we are going to make in this. We are not going to derive anything. So, reverse redrawing schematic is shown in this particular figure. Okay. So, it is the same cup which is drawn. So, we have shown this cup now, the same cup, this cup now, there is a cup wall and there is a cup bottom which is coming here, right. So, this cup is formed. Okay. So, we are going to pick up the same cup. Okay. So, you have a sheet, the sheet is drawn into a cup. Okay. Now, this cup is actually further drawn into another cup, either by forward redrawing or reverse redrawing. Now, with respect to reverse redrawing, the main point is when you go to the next stage, you are going to keep it upside down. You are going to keep the same cup upside down and punch will come from this side. And punch will come from this side. This is going to be your punch. This is going to be your punch. Okay, this is what you are going to do in reverse redrawing. RRD, let us say, in reverse redrawing, your punch will be kept upside down. Reverse redrawing is shown in this figure. In this, the cup is turned inside out. Okay, that means your cup wall is going to come down. The cup wall is actually hanging down. In the previous case, the cup wall is going to be like this. So, the cup wall is actually like this. In this case, it is actually going to come down like this. Okay, and this will be kept on the retainer. Okay, and punch is going to touch this surface and it is going to be displaced, and you will see that of course, the first portion that will form is basically the cup bottom. After that, this cup wall is going to get formed. So, now if you push the punch down, it is all about the material coming from this side and is going to become a cup wall like this. It is going to get displaced in this way to form a final cup which contains only cup wall and the cup bottom. That is all. Okay. So, since the cup bottom is already formed, so it is all about converting this wall to this wall via one bending, one unbending. One bending, The material is actually bent here and then unbent to keep a cup wall. So that is the only difference. So 1 plus 1. In the previous case it is 2 plus 2, here it is 1 bent and 1 unbent. So there is only 1 bent and 1 unbent operation. Therefore the drawing force F is reduced as compared to forward redrawing. Okay, and what you need to do is actually, so all equations remaining same. So instead of 2 pi r2 into t phi plus 4 delta t phi, you have to write 2 pi r2 into t phi plus 2 times del t phi, okay, because it is only two activities, 1 bent, 1 unbent, 2 del t phi, that is all. That is the only difference you have here. And then finally, you will get this particular equation. This is a drawing force in reverse redrawing by considering change in tension. Only difference is 2 pi r2 sigma ft ln of r1 by r2, everything remains same, plus t by 2 phi. This 2 gets into this denominator. So instead of t by rho, okay, so t by rho becomes t by 2 rho or 1 by 2 times rho by t. Okay, that is the only difference you have here. So if you put appropriate values inside this, into these two equations, you can find out that the drawing force in reverse redrawing is actually smaller than the forward redrawing. Okay. So this is what the expressions that we can derive for punch force during forward and reverse redrawing in a very simple way. The only thing is this equation is not derived. We are going to assume this, or maybe like we have, this has been taken from a different chapter, different source, and then that gets added to T phi to get F. Okay. So another small section, okay, which is also important practically, that is your wall ironing during deep drawing. Okay. We are not going to derive anything. What we are going to do is just some important new note, some bullet points type. This is what we are going to understand from this. So wall ironing basically occurs. Okay. Wall ironing is actually a phenomenon that will happen during deep drawing process, cup deep drawing. It occurs when the clearance between the punch and the die is less than the initial thickness of the cup wall. The clearance between this is your punch, let us say, okay, and this is your die. The clearance between the punch and die is less than the initial thickness of the cup wall or initial thickness of the sheet. Okay. So if cup wall basically means you are going for further drawing. If it is initial thickness of the sheet means it is a first time drawing. So if the clearance is less, then wall ironing will happen. Wall ironing will happen means like this. You can see that a cup of T1 thickness, okay, is coming into the die, okay, and you will see that because the clearance is less, okay, the clearance is less, you will see that the cup wall is actually forged. The cup wall is actually forged, okay, in this location or in this location, either way you can look at the cup wall is actually forged inside this, and thickness gets reduced and becomes T2 in the bottom cup wall. So when the cup is getting drawn, okay, or when the sheet is getting drawn, T1, a larger thickness, is going to become a smaller thickness to accommodate the material in the cup wall itself, because the material cannot go anywhere. It has to get accommodated because of lesser clearance. Okay. So generally the clearance should be slightly larger than the cup wall thickness or sheet thickness, but here it is less. Then the decrement in clearance will take care of thickness reduction T1 to T2 will be accommodated accordingly. Okay. So anyway, the point is the cup with the T1 thickness is going to become T2 thickness, where T2 is going to be smaller than T1. That is nothing but your ironing operation. Okay. So now what will happen is, suppose this material comes with V1 velocity, okay. So it moves with V1 velocity, and at the exit, okay, you will see that the material, actually the cup will go with the punch velocity only, Vp. So the velocity is not going to remain same as V1, it is going to be Vp. So the cup wall after the die, if you monitor, this velocity is nothing but your Vp only. So the velocity of the material as it exists, the die, Vp is same as that of your punch velocity. Whatever punch velocity you are giving, that would be this. Okay. So now what we can do is like during ironing, since there is no change in volume and the rate at which the material enters the die equals the rate leaving the die. So we are going to bring in velocity, that is why V comes into picture, okay, and the rate at which material enters the die will be same at the initial and at any intermediate level. So you can write 2 pi Ri T1V is equal to 2 pi Ri T2 into Vp. So you will see that V1 is connected to T1 and Vp is connected to T2, and you can say that 2 pi Ri T1V will be equal to 2 pi Ri T2 Vp. Okay. So, which will give you a simple relationship. V1 is nothing but Vp times T2 by T1. Okay. And your T2, which is your second thickness, this is going to be T2 is going to be smaller than T1. So, hence Vp would be greater than V1. Here you would see that Vp is greater than. The punch moves faster than the entry material. Okay, the punch moves faster than the entry velocity. So, your output velocity would be larger than the input velocity. And if you look into the interaction between the cup and the die, okay, let us assume that maybe like Q is nothing but your normal force acting on the two interfaces. One is on the inner surface, that is here with respect to the punch, and on the die side, this side with respect to the die. Okay. So, let us say the reaction force is the normal force is Q, then friction force can be obtained by mu P times Q here, mu D times Q here. Okay. I am not saying mu here, mu P, coefficient of friction on the punch side, coefficient of friction on the die side, they could be different. Okay. And you will see that the direction also got changed. Okay. So, here your friction force is acting a downward direction, and because of the thickness reduction, this fellow will act against it. This fellow is going to act against it. Okay. So, two things, coefficient of friction is also changing and the direction is also changing. So, here it is mu P into Q, here mu D into Q, here it is downward, here it is upward. Okay. So, this fellow is actually going to help. This is going to aid the drawing. Okay. And the friction force between the punch and the sheet is actually downwards. This assists the process, this aids the process. So, what you need to do is advantage during ironing if you want to pick up. Okay. So, since you are on the punch side your mu P into Q, that mu P is going to help you. Okay. So, this mu P has to be kept larger than mu D, because this is actually going to help us. So, the helping factor, the aiding factor should be larger than the other one. So, mu P has to be kept larger. So, mu P has to be kept larger than mu D. That generally what people do is they roughen slightly, punch is actually roughened slightly, so that even if you put lubricant, there are chances of mu P being higher than mu D. And on the opposite side, on the die side, you put lots and lots of lubricant. Outside of the cup is heavily lubricated. Outside of the cup, that is this side, outside of the cup means this side is heavily lubricated, and this side you will see that it is roughened, the punch is roughened. Okay. Or maybe you do not put lubricant, something like that. Okay. So, that your mu P is always greater than mu D, mu P is greater than mu D. Okay. So, these are some important note points. Okay. So, required for your wall ironing operation. Okay. So, you can note down, this is one small section, we are not deriving anything here, any equation here, this is just ironing operation is important, deep drawing, and though ironing operation is unwanted, but sometimes you want to control the cup wall thickness, you deliberately allow wall ironing to, so that you have particular thickness in the cup wall. While doing so, you have to keep these things in mind, that is the whole point. Okay. So, mu P should be greater than mu D, and you purposefully do it like you roughen the punch, and then on the opposite side, on the outside of the cup, you put lots and lots of lubricant, okay, to maintain this particular situation. So, with this we are completing this particular chapter on deep drawing, but before that let us do quickly some 2-3 important problems, small problems which will be useful for us. The first one is, a cup is to be drawn in a deep drawing operation, fine. The height of the cup is 75 mm, the output height is 75 mm is given, and its inner diameter is 100 mm. Okay. So, cup height is 75 mm it is given, and the inner diameter, or maybe you can take radius also, let us take inner diameter as 100 mm. These two are given. The sheet metal has got thickness of 2 mm. So, T naught you can keep it as 2 mm. The blank diameter is 225 mm. Blank diameter means you can maybe like you can say D naught as a 225. So, 225 becomes 100, that is the point. So, 225 becomes 100. So 225 is the sheet diameter, that becomes 100 mm diameter cup. Okay. So if that is the case, you need to calculate few things. One is the drawing ratio, reduction, thickness to diameter ratio, and converting this 225 into 100. Okay, this is the sheet diameter, this is a cup diameter. Is it possible or not? Whether the operation is possible or not. Okay. So draw ratio we know, it is very simple, 225 by 100, 2.25. Reduction is generally given by 225 minus 100 divided by that reference, that is 225, which is about 0.56, and keeping it as 56%. So 225 minus 100, okay, so that will tell you the difference divided by the reference, that is 225, okay, which is nothing but 0.56, approximately 0.56, which is about 56%. Okay. This reduction is somehow similar to R1 by R2. So somehow similar to R1 by R2, but not exactly same, somehow similar to R1 by R2. Okay. So anyway, so now this second one is calculated, and the thickness to diameter ratio, it is straightforward, T by D. So T is given, okay, 2, D is actually 225, it is about 0.009, you can check it. Okay. And these all are calculated, that is fine, but is the operation feasible or not? It is said that it is not feasible because of the following reasons. One, what are they? Though we know all these are available, okay, there are certain design criterion for us. Generally, it is said that draw ratio, we have also pointed out that it should be 2 to 2.2. 2.72 is, again I am coming back, 2.72 is a theoretical one. Practically speaking, 2 to 2.2 should be good. Okay. Limit drawing ratio. Okay. So now you will see that this is 2.25, which is greater than 2.2. Okay. Even if you be little bit conservative, let us keep it as draw ratio requirement is 2. Okay. Then it is greater than that. So it is not possible. Reduction, generally it is said that it should be closer to 50 or less than that. Generally, these are conditions we have not seen. It is just for us to record now. Okay. It is for record now. So reduction should be less than or equal to 50, but in this case you will see that it is greater than 50, and T by D should not be very small. It should generally closer to 1% or more than that. If you convert this into percentage, you will see that it is less than 1%. Because of that, this operation of converting a sheet into a cup would be unsuccessful. So we say it is not feasible. We say it is not feasible. So we are picking up three conditions. One is draw ratio. Maybe you can keep it closer to 2. Since it is greater than 2, it is not possible. Reduction should be closer to 50. More than this, it is not possible. T by D is actually very small, which is also not comfortable, which is not good. So this is not possible. Okay. So though these values can be calculated, but finally the process is not feasible. Suppose if you want to change this, suppose 225 is not the case. Initial sheet is actually, let us keep it as 175. That is your second problem. Question 2 is same as previous problem, but sheet diameter is 175. What is the draw ratio? 175 by 100, 1.75. Fine. It is less than 2 or less than 2.2, accepted. Reduction, 175 minus 100 divided by 175, which is about 43%, less than 50, it is fine. T by D, okay, is greater than 1%, it is not too small. Okay. 2 by 175 is about this. In percentage, it is slightly greater than 1. It is also accepted. So all these three are fine. Okay, but still this drawing is not feasible, because with 175 mm sheet diameter, you cannot make a 75 mm cup. 75 mm, this is a height you have to form. No? Then we let us calculate height and find out. So height is this equation we derived just now. Ri by 2 into R naught divided by Ri whole square minus 1. So it is Ri is diameter is 100, so it is 50 by 2, okay, into this is 175 diameter, isn't it? So R naught is 8, so it is 1.5 divided by 50 whole square minus 1 would be 51.5 mm. So if you use 175 mm initial diameter of the cup, though these design conditions are acceptable, this is fine, but still the cup you cannot make it, because the material itself is not sufficient for you to make a cup of height 75 mm. Why? Because as per this equation, height is that we get is only 51.5 mm, which is less than 75 mm cup that is required. Okay. So, this process again not feasible, not because of the same condition, but because of the scarcity of material. The material is not, diameter is not sufficient for us to make. So, this type of simple problems can be solved from this. So, let us go to the third problem. So, a fully work hardened aluminum sheet of 100 mm diameter and 1.2 mm thickness, it has got a constant flow stress of 350 mm. Okay. So, your R naught diameter is given, but R naught anyway you can get, thickness is also given, okay, which is 1.2, flow stress is given, let us say take it as sigma f is equal to 350 MPa, constant thickness, so no problem. A cup diameter is made of, let us say Ri, that is 50 mm diameter cup is made. Blank holder force is given as 30 kilonewton, which is nothing but 30,000 Newton. Friction, coefficient of friction is given as 0.1. So, what is the question? You have to find H and maximum punch force, which is what we calculated just before, which is nothing but F. So, H is again same formula, Ri by 2 into R naught divided by Ri whole square minus 1, which is nothing but Ri is given, what is it? Cup height is 50, that is diameter is 50, okay. So, 25 by 2, so 50 by 25, the whole square minus 1 is going to be 37.5 mm. So, you can calculate it and find out, it would be 37.5 mm height. So, with this particular aluminum sheet of 100 mm diameter, 1.2 mm thickness can be converted into a 50 mm cup. It has to be deep drawn. Okay. So, now they are saying that what is the final height? This could be the final height that can be drawn for this particular type of material. Okay. Sorry, this is 50 mm cup diameter. Sorry, this is not height. No, this is not height. This is a cup diameter. Yeah, cylindrical cup of 50 mm mid wall diameter. So, cup diameter is 50, correct. So, that is what we are given as 25. Okay. So, final height is formed is only 37.5 mm. So, now let us come to the punch force. This formula is already we derived 2 pi Ri T naught into sigma phi. Alright. So, this equation we have derived in the previous class, in the previous lecture. Okay. Sigma phi was derived. Sigma phi was derived by us. What is sigma phi? Sigma phi is this particular one, no? You remember this? Okay, this particular one. Sigma phi is nothing but sigma f ln of R naught by Ri plus mu b by pi R naught T naught into exponential mu pi by 2. This is, we made it in general now. We removed 1 by eta before this. So, 1 by eta was there before this. So, 1 by eta was there for the derivation that we have removed, and then we kept a sigma f average, which is also removed now. So, okay, all are removed, and then it has gone back to R naught and T naught. It has gone back to R naught and T naught. Okay. So, we have not really derived the punch force for conventional deep drawing, rather we derived only sigma phi, cup wall stress from sigma R. Okay. That is what we derived as a sigma phi. So, now what you can do is you can multiply by 2 pi Ri into T naught into sigma phi to give 2 pi Ri into T naught into sigma f into ln of R naught by Ri plus 2 plus mu b by pi R naught T naught exponential mu pi by 2. Okay. So, now here what is Ri? So, Ri is 25 mm, T naught is your 1.2 mm, sigma f is 350 and Ri is known. What is R naught? R naught is your same 50. Ri is again 25, I think you can write. So, B is 30,000 Newton, R naught is again given, T naught is again given 1.2, exponential mu is 0.1 into pi by 2. So, if you substitute all these values, you will get this value, you can check it, it is 57 kilonewton. This much of maximum punch force is required to draw a cup of this particular material. Okay. So, this much force is punch force is required. So, remember we have derived punch force equation only for redrawing, not for regular drawing. So, this problem will give you an idea of how to calculate the punch force provided you have sigma phi, which is already derived by us before. So, that is not in this, this is sigma phi, no. So, after this all these things we derived it. So, anyway, so that you can look into it. So, this is one way to solve this particular problem, you can check it. So, with this we stop. Let us go ahead with the next section.